Thanks for coming to this session. My name is Tomas, and I'm going to be talking about CloudSearch and how we use Solr. If I get this on the screen. There we go. So I am a software development engineer at A9. A9 is the Amazon subsidiary that works with all the search platforms for Amazon. I am a part of the Amazon CloudSearch team, and I recently become a Solr committer. So this is what I'm going to be talking about today. First of all, a brief introduction about what is Amazon CloudSearch. I'm going to show how we are deploying Solr in Amazon with Amazon Web Services. Some configuration internals that I think are important to the way we to let CloudSearch work the way it works with Solr. And finally, I'm going to describe some of the contributions that we have done since we started working with Solr in the CloudSearch team, and we have contributed back to Lucene and Solr. So, for those of you who don't know, Amazon CloudSearch is the Amazon Web Service for search. It's a fully managed service that allows you to create domains, and from there, upload documents and do searches. What we are trying to solve with CloudSearch, first of all, the operations around setting up your search application. You don't need to install any hardware or software. The only thing that you need to start using CloudSearch is Amazon Web Services credentials. We try to solve scaling so that you don't have to worry about scaling your domain for data or for traffic. If you are using Solr or Elasticsearch or any other engine on top of Lucene, you know that every couple of months there are new versions that come with new improvements, new features, but you need to upgrade to get those. In CloudSearch, we do those upgrades in the background without any downtime, so you don't have to do those upgrades. And finally, Amazon CloudSearch is fault tolerant, so you don't have to architect your search application to be fault tolerant. CloudSearch is already. So when we launched CloudSearch, it was initially working on top of Amazon A9 internal engine. That is the same technology that works with works where Amazon.com searches uses, but we decided to migrate to Solr. Some of the reasons are the typical open source reasons to use open source, like easier to get started for new engineers or software tested by the community. But also, Solr comes with out-of-the-box support with most of the features that most search applications need. So all we have to do is expose them. For example, when we launch CloudSearch on top of Solr, we launch with like 30 new languages that for us, it would have been very difficult to implement, but because it is already in Lucene Solr, it was very easy to expose. Finally, because it is an Apache Software Foundation project with a defined process to contribute back, we didn't have to fork Solr. We used plain Solr, the official release. We do have some custom components that are pluggable, but that's all we need. And whenever we have something that we think belongs to Solr, then we were able to contribute that back. So this is the highest view that you can have from CloudSearch. So we have a configuration service. That's where you are going to be doing all your configuration requests, where you're going to do API requests to create a domain or to configure it, like adding fields or making your domain multi-availability zone. Or all those configurations are going to be requests to the configuration service. You can also interact with the configuration service. So you can interact with doing HTTP requests, but you can also interact using the console or Amazon AWS SDK or command line interface. All of those things are going to go through the configuration service. When you create your domain, we're going to give you 2 endpoints, one for uploading documents and one for doing search. And this is what your domain is going to look like. It's going to be an ELB with some EC2 resources in the background. This is just yours, and you don't share it with anyone else. So as I said, you are going to have a document endpoint. The document endpoint is going to be pointing to this ELB, and the ELB is going to redirect the request to any of the EC2 resources in the background. On the EC2 instance, we are going to have what we call a document service. This document service will get the request, and it will validate it. And if everything is OK, it's going to store the documents in S3 and store some metadata in DynamoDB. Once this is done, we already respond with a 200, and we are not going to ask you to re-upload those documents ever again. You can even do some configuration changes to your domain. But because we already have the data, we don't ask you to upload that document again unless you need to update it, right? In the EC2 instance, we also have what we call an updater process that is going to be looking at those DynamoDB changes. And whenever there are new batches that need to be applied, it will download them from S3 and push them to Solr. So that at this point, they are available for search. The search endpoint is also pointing to this ELB. And the ELB will also send the request to one of the EC2 instances in the background. However, the query side is much easier. We let Solr handle the query. CloudSearch API is different than Solr API. So we do have a thin layer around Solr that translates CloudSearch API to Solr API. It is only pluggable components. Like we only use for that request handlers or search components. We don't have to do any custom code that's not pluggable. So as I was saying, CloudSearch will scale for traffic. The way we do that is by using auto-scaling groups. The auto-scaling group is a feature that EC2 already ships with, has, that when, with some settings, you can tell it that when the CPU utilization is high, it should launch new instances. And that's exactly what we do. So we launch new instances that make copies of the index and start serving queries whenever they are ready. For scaling for data, what we do is, first of all, we're going to try to put you on a larger instance type. So when you create your domain, by default, you're going to start on a small instance type. As you continue adding data, we will put you on larger instance types, right? At one point, when there are no larger instance types for you to use, what we do is we regenerate the index and split it into multiple shards. For this, we use EMR, another Amazon Web Service that will launch, it's called Elastic MapReduce, that will launch a Hadoop cluster where we regenerate the index into as many partitions as we want. We could, in this case, we're generating more partitions, but it also works the other way. Like, if you delete a lot of data, you could go to less partitions. So if you don't say anything in your configuration, you're going to go to automatic scaling. The way automatic scaling works is by giving you the start with the smaller instance type, a single partition, and a single replica. But you can change that if you are expecting, if you want to have more replicas, for example, or if you want to start with a larger instance type, or even if you want to start with more partitions because you're going to be pushing a lot of data, you can manually change those settings. Also, some changes in your configuration we will be able to regenerate your index after changes in your configuration without asking you to re-upload the data. For example, let's say you defined a field and you defined it as a text field, but then you realize that you actually want to facet on this field, so text field is not good. So what you can do is go through the console, create a new field that's for facet, do a copy field, and you don't have to re-upload the data. You don't, for Solr to do that, you have to re-index. But we can do the re-index for you with an EMR job, and whenever your configuration, your new index is ready, we're going to deploy it. And all those changes, these EMR jobs, these new instances, everything is done in background so that there's no downtime. The new EC2 resources that we launch are going to remain unused until they are ready. Once they are ready, we are going to start sending the traffic to the new resources. If anything goes bad and those resources do not become available in a healthy way, then your traffic will continue to work with the old domain, with your old resources, right? This is the same for upgrades. So we can do upgrades, and if something goes wrong and we cannot put you on the new version, the domain is going to stay on the old version working as it was before. So one of the challenges that we face in CloudSearch is that we don't have a single search application. We have lots of them. So we rely on lots of tools like management and for operations, for monitoring, but we also require that the configuration that we set for those Solr instances is good to all of our is good to all domains, right? It cannot be just good for a couple or for some case. This is one of the challenges that we face in CloudSearch. Before I joined CloudSearch, I was a Solr consultant for Lucid, and the typical question that we would get is, how much memory should I assign to the Solr process? And the answer was always, it depends, because it really depends on the fields that you define, on the types, on your data, on your query pattern, what you are going to be using with that data, what you're going to be doing, where you're going to facet, sort. So the way to resolve it in Solr is test it, right? Upload some data, upload all your data, start doing the queries the way it's going to work in production, see how much memory you require, and try to assign enough JVM so that you don't get out of memory errors. But at the same time, you don't want to define too much heap to the JVM, because that takes away memory that could be used for the file system cache, plus it makes it more difficult for the garbage collector, right? So part of it we can do with CloudSearch, but part of it we can't. So we don't know exactly what the data is going to look like or what the query pattern is going to look like. So the way we resolve this in CloudSearch, this is the schema section of the Amazon Web Service Console for CloudSearch. And see how we ask the customer to, when they define fields, we ask them to specify the field and the type, the name and the type, but we also ask them how they are going to be using those fields. So we're going to use it for facet, for search, for return, for sort, for highlighting. And based on that, we decide what field attributes to set to each of those fields. So the important part here that I wanted to say is that we always decide to use doc values if we're going to need them. Like if the user has indicated that they want to use a field for facet or for sorting or the ID, those fields are always going to be using doc values. Doc values were introduced in Lucid 4.0 and Solr 4.2, and since then they have had improvements on almost every version. They are essentially document ID to value mapping, like the inverse of the inverted index. And this structure is used for faceting, for sorting, the way it was done before doc values, and that can still be done today is by using the field cache. However, the field cache has some problems. Like, first of all, the field cache needs to be generated by inverting the segment with every searcher reopen. The document values instead are generated at index time. So whenever a new searcher is reopened, all you need to do is read the file, right? And also the doc values are much more memory efficient. So the field cache keeps everything in memory, even the values of the field. All the distinct values for the field are going to remain in memory. Doc values, on the other hand, will only keep part of the structure in memory and the other part in disk. So it's much more memory efficient. So this allows us to set a JVM. The heap size is relatively small. We rarely use more than 4 gigabytes for the JVM memory. So this allows us to leave most of the RAM to the file system cache, and allows us to, it doesn't give us problem with the garbage collector, or doesn't require us to do a lot of tuning of the garbage collector. So I did a very informal experiment in my Mac. I uploaded like 16 million documents, and I created 2 schemas that are exactly the same, one with doc values and one without doc values. And I started a process that would upload 1 document every 1 second. So after those 16 millions are indexed, of course. And then another process that would run queries. I wanted to see how the memory would look like. I used 512 megabytes for this on plain Solr 4.10.2. So the first chart is the with doc values, and all of those are young generation garbage collections, except for that one in the middle. And that's how it should look like. The second one, all of those are full garbage collections. Most of these are full garbage collections, and the problem is that in this case, it's virtually running out of memory. So that's why it's doing all the garbage collection. It had to do, when I check the stats for these 2 runs, the test took like 18 minutes. With doc values, it used 4 full garbage collections, and the total time spent in garbage collection was around 3.7 seconds. While without doc values, there were much more full garbage collection events, and the time for garbage collection was huge. Of course, I mean, this is a bad configuration for, the heap size was not enough for the second case. That's why it has so many full garbage collection, but that's exactly the point. So you need more heap in that case. We also use a custom filter cache that's using a caching wrapper filter. This allows us to have a filter cache that is per segment, instead of a Solr filter cache that gets flashed for every searcher we open. We currently reopen searchers every 1 second. And on top of that, we can enable or disable the filter cache based on stats. So we keep stats of the hit ratio, and when we see that the field cache is not being affected, we just don't use it. We do very light warming. We use the simple merge segment warmer. That's a Lucene class that initializes the structures of the newly created segments after a merge, so that whenever you need to use that segment for search, it's already warm. And we also, so Solr requires for stuff like faceting the doc values top level cache. So we warm those using custom searcher listener, that whenever a new searcher is open, we read those doc values. The way you would typically do this is by using static warming. For us, that would be difficult because we don't know exactly what the queries of the customers are going to look like. It would be difficult to do this. And we don't do any Solr auto warm. We use caches. We use the other Solr caches, but we don't warm them. This configuration has proven us to be very good for near real time. As I said before, we open the searcher every 1 second, and we haven't seen issues with that, not even the overlapping searchers on deck warning. And finally, I would like to talk about some of the contributions we have done to Lucene and Solr since we started working on this version of CloudSearch on top of Solr. We have done also a lot of bug fixes, but also these are some of the feature additions that we did. First of all, expressions. So expressions allows you to set arbitrary scoring functions written in JavaScript. I mean, you could use something different than JavaScript, but you have to create your own compiler for that because the only available right now is JavaScript. Expressions can refer to other fields or other expressions, and they are compiled at runtime, so they are very fast to run. And expressions has been added to Lucene. I don't remember in which version, but some time ago. They are still not in Solr. This is how you would use expressions in Lucene. So you define your expression and you compile it, and then you bind the variables that you are using to, in this case, sort fields, and then you can use that expression for sorting. As I said before, expression is still not available in Solr. But in CloudSearch, this is how it looks like. So in this case, we define the expression rank 1 that uses a score multiplied by this logarithm popularity, and then we sort on that expression. In Solr, I guess it's going to have some similar API, but it's still not there. So we also contributed Jack's simple query parser. This parser does human-readable reads queries. Sorry, and the idea behind this parser is that first of all, it's very simple. Second, it doesn't error. So if the syntax that you provide is not correct, then it will try to generate a query that's the best it understands, but it won't error, right? It can also enable and disable operations. So for example, if you know that prefix queries are very bad for your search because they use too much resources and you don't want to support them, which you can disable the prefix query so that the simple query parser will never generate a prefix query. And this over there is Jack. And if you can see, he uses a vertical keyboard. And that's how the simple query parser was built. This is an example of how you use simple query parser in Solr. This is a simple query of iPod on the text and cat fields, and it generates a Boolean query. This is the example that I was saying before. It's IPO star, and you list the operators that you want to support. In this case, I'm listing all the operators, so everything is supported, and the query generated is a prefix query, IPO star. However, in the second example, I remove the prefix from the list of operators, so the query generated is now a Boolean. It's just a term query for IPO. What happened here is the IPO star. So the output of the query parser was IPO star on the text field, but then the analysis removed that star, right? So it considered just a regular character, the star. This example may be simpler to see. So I'm doing a query for quote iPod, and then I accept all the operators, and it generates a phrase query. However, in the second case, I remove the phrase operator, and the query generator is a Boolean. It's a Boolean query. We also contributed the suggester. Suggester is FST-based. It supports setting an analysis scheme. It supports sorting your suggestions on expressions. And as I said, expressions is still not in Solr. However, in the suggester, you can use expressions. It's supported right now in Solr. And the response for suggestions are documents that match your suggestion, not simple terms. Something like if you have used like IMDb, it's like just start typing and it will tell you like this movie is what you're looking for. We also contributed back interval faceting. Interval faceting is yet another faceting method, another faceting implementation. So the functionality of the interval faceting is very similar to it can be achieved right now by doing facet queries on using range queries on those facet queries, right? It essentially counts the number. So given a set of intervals, interval facet will count the number of documents that have at least one value in those intervals. So I was saying that the same functionality can be achieved by using facet query, but the implementation is completely different. So facet queries and range queries, they both work on a similar way. They do filters on each of the intervals, right? So in the facet queries, it will do a filter with that query. Range facets do a filter for each of the intervals. This works okay in some situations and not so good in some others. Because those filters are going to use filter cache. So if the query if your index is somewhat static, the index doesn't change that much, you don't reopen searches that often, then this is fine because the filter cache is going to be pretty much pretty effective. Well, the only problem is that you'll be populating the filter cache with all these facets. If you have too many, it may be a problem. But anyway, so in that scenario with a static index, facet query and ranged facets can work very well for you. However, when your index is very dynamic and you reopen the searcher every 1 second as we do, and every 1 second a new search, I mean, because there are many updates, every second a new segment is created, the filter cache is flashed, then you will start seeing problems, right? And also, another problem with this is that it will generate one filter per interval. So if you have too many intervals, even if they are all in the same field, it's going to be doing one filter for each of those. So interval faceting works using doc values. It iterates the doc values and well, counts the number of documents that match each of the intervals. This way, it works much better for cases where you have multiple intervals in the same field. So this is the syntax of how it would work. So you say, for example, I'm going to facet on the field popularity, and I want to set these 3 intervals from 0 to 4, 4 to 7, and 7 to infinity. And it will return the number of documents that match each of those intervals. In the same way as with facet query, you can specify a different key for each interval. So in this case, for example, I will say 0 to 4 is bad, 4 to 7 is average, and good is 7 to infinity. And the return value is going to look something like this. So the reason why we implemented this instead of using facet query is that, as I was saying, it works much better in most cases, right? So if you are in the static case, the filter is fine, but on the other cases, this is not that good. So I evaluated the performance on, this is a real index of 100 million documents and some production queries that have around 40 intervals each. You can see how in average, the intervals is much better than filter query. This is query time, so lower is better. You can see how the average of intervals is much better than facet query. However, if you go to the lower percentiles, they are almost the same or even better for facet query. Those are the cases where your filter is coming from cache. If you go to the higher percentile, like the 90th percentile, you see already that the intervals is doing better than facet query, right? But if you go to P99, to the 99th percentile, you see that intervals is doing extremely good compared to facet query. Facet query is doing terrible. And this was the case we were hitting. If you think you can live with this, I mean, you can live with a small percentage of your queries being slow, it's fine. However, if you have an index that's on multiple partitions, on multiple shards, and you start seeing some of these in the different shards, it's going to make your, the overall search time is going to be very bad. That's all I have. Thanks. I think we have 1 minute. Any questions? Yeah.
How do you deal with clients or users with this that cause their Solr to blow up?
Can you? I cannot hear you.
How do you deal with situations where you have users or users in the system that cause their Solr instances to just blow up, like blow out memory or anything like that? How do you deal with those scenarios?
Well, we haven't run. So if something goes wrong with the Solr instance, the auto-scaling group is going to put that instance out of service and is going to start a new one. We haven't seen like out-of-memory errors that would cause this. But for example, if you have a very high peak in request and the auto-scaling group is not fast enough to start new instances, you're going to get some errors until the new instances are available. Yep.
Are you going to expose the Solr APIs? Is there any planned feature for that, or it will always be a wrap with the CloudSearch
At this point, this is where the API is different.
But is there any plan in your roadmap or something?
I cannot, I mean, I won't be able to talk about the roadmap, sorry. Yeah. I don't have more time, sorry. Thanks.